Well, what if the data is not categorical? What if the data is quantitative? Then we cannot use proportions. Right? We have to use means. So just like previously, we're not going to be testing or finding an interval for one mean. We're going to be finding an interval or running a test for the difference between two means. So we have two populations, 1 and 2. What is the parameter of population 1? Well, it's mu1. The parameter for population 2 is mu2. What statistics are we going to be using to estimate these? Oh, well, x bar 1 is the unbiased estimator of mu1. X bar 2 is the unbiased estimator of mu2. The sample size 1, n1, and the sample size for population 2 is n2. Okay. What does this sampling distribution look like? Well, the data is approximately normal when central limit theorem. Okay, so how do we know if it's normal? How do we know we can use z-scores in our favorite picture? Okay. If the data is approximately normal, so by the central limit theorem, which says that n1 is greater than or equal to 30, and n2 is greater than or equal to 30, or they tell us. So if they tell us the population is known to be normal, we're good. Or if the central limit theorem applies, which our n's are greater than or equal to 30, then the data is approximately normal. Well, what is the mean of x bar 1 minus x bar 2? So if I want to find the difference in the sample means, I simply subtract them. So the mean of all the different possible samples I could find would be mu1 minus mu2. And then the standard deviation. When am I allowed to use this formula for standard deviation? If the population is at least 10 times the size of the sample, or as the book refers to it, the 10% condition is met for both samples. So again, it looks very similar. It's just the standard deviation formula. So the standard deviation of x bar sub 1 minus x bar sub 2 is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So just like in the proportions, all we're doing is taking the standard deviation from one sample and adding them together and square rooting that to get the entirely new standard deviation. Okay? When are we allowed to use this? If it's independent, meaning the population is at least 10 times the size of the sample. All right, so here we go. Let's do it again. Okay? A fast food restaurant uses automated filling machines to pour its soft drinks. The machine has different settings for small, medium, and large. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine is normal with a mean of 27 and a standard deviation of 0.8. When the medium setting is chosen, the amount of liquid M dispensed is normal with a mean of 17 and a standard deviation of 0.5. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled using the large setting of 25 cups filled using the median setting. Let x bar sub L minus x bar sub N be the difference in the sample mean amount of liquid under the two settings. Okay. What is the shape? Okay, so for part A, normal. How do I know? They told us. They tell us the population is known to be normal. Okay. What is the mean? Well, as we said before, that the mean of x bar sub 1 minus x bar sub 2 is just equal to the mean of 1 minus the mean of 2. So the mean is 27 minus 17, or the mean is 10. Okay. And then calculate and interpret the standard deviation. So the standard deviation says take the the standard deviation of x bar 1 minus x bar 2 says take the square root of S sub 1, which is 0.8 ounces, squared divided by N sub 1. So there was 20 cups filled using the large, plus the standard deviation of number 2, which was 0.5 squared, divided by how many from the median, which was 25. So I do this work and I get 0.205 ounces. What does this mean? Interpret this. That the difference between the large cup minus the median cup and the sample mean varies by about 0.2 ounces away from the mean of 10 ounces. So on average, each difference is about 0.2 ounces away from 10 ounces. That's the interpretation of the standard deviation. All right, so we've seen the sampling distribution. Let's look at how we construct a two-sample T interval. Again, a lot of this page was messed up. You see all these red, just ignore them. Just look at the other formulas on this page. You'll see this wrong stuff written in your reading for this chapter as well. So please refer back to this to see what it is that you need to ignore. All right, so how do we calculate the confidence interval? Once again, every confidence interval in the world is estimate plus or minus margin of error. So how do we estimate the difference between mu1 and mu2? Well, x bar 1 minus x bar 2, since x bar is the unbiased estimator of mu, plus or minus t star times the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. So again, this is just the standard deviation. So remember, estimate plus or minus margin of error. Everything behind the plus and minus is the margin of error. Everything behind the star is the standard error. And the standard error is just the standard deviation. Okay, so it's T. What goes along with T? Anytime we see T, it's T means we need degrees of freedom. How do we choose degrees of freedom? Well, what we've always done before is n minus 1. Well, now we have two n's. So the degrees of freedom is the smaller of the two, n1 minus 1 and n2 minus 1. Whichever one's smaller, that's our degrees of freedom. The smaller of the two gives us the degrees of freedom. So we're going to try to estimate with confidence. Okay. Now we have T star, so we know we need degrees of freedom. Then down here, are we allowed to do it? Well, is it random? They tell us or they don't. Independent, is the population at least 10 times the size of the sample? We need to check for both. Normality, large sample, does the central limit theorem apply for both n sub 1 and n sub 2? Or do they tell us they're both known to be normal? Same conditions, but now we just have to check them for both. All right, so let's do it. The Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to the foresters who study the area is how do the sizes of the longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height in centimeters. Here are summary statistics and comparative box plots of the data. Based on the graph and numerical summaries, write a few sentences comparing the sizes of the longleaf pine trees. So it appears that the southern trees are larger and more consistent with a smaller standard deviation. Okay. Based on the graph and numerical summaries, comparing the sizes. So the south seems bigger than the north on average. The center is much larger in the south than it is in the north. The spread of the north is greater than the spread of the south. Okay. Shape. They're both approximately normal since n is greater than or equal to 30 by the central limit theorem. If you look at the box plots, however, they don't look altogether normal, the original data. Okay. All right, part B, construct and interpret a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves of the Wade Tract Preserve. So what are we going to do? Okay, we're going to construct a 90% confidence interval. 90% confidence interval for what? Okay. For mu sub 1 minus mu sub 2. So what? What is mu sub 1 and mu sub 2? So mu sub 1 is the true mean DBH for all trees in the southern half. What's in sub 2? The true mean DBH for all trees in the northern half. Okay, I know it's a lot of stuff, but it's not that hard. All we're doing is paraphrasing what's in the problem up here. Okay. All right, so what am I going to do that? How am I going to do it? Oh, you know what? I bet I'm going to do a 2 sample T interval. So 2 sample T interval. Am I allowed to do it? Oh, random. Yes, random. They tell us. Is it independent? Is the population at least 10 times the size of the sample? Yeah. I'm sure there are more than 300 trees in each section of the forest. Normal? Yep. Since n is greater than or equal to 30, they're both normal by the central limit theorem. All right, so step 1, what are we going to do to find the parameter? Step 2, are we allowed to do it? So we know what we're going to do. We know that we're allowed to do it. Now, let's do it. So let's construct this interval. It's going to be, remember, x bar 1 minus x bar 2 plus or minus t star times the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Let's start getting the data. X bar 1, 23.7 minus x bar 2, 34.53 plus or minus t star. Uh-oh, I don't know how many degrees of freedom this problem has. So remember, it's the smaller of the two. Well, they're both 30. So my degrees of freedom is 29. So let's go to our favorite table B here, and let's see if we can find the T-star value at 90% confident for 29 degrees of freedom. So let's drag this guy over here, and 29 degrees of freedom. Oops, I need to see the bottom. And I want to be 90%. 90% at 29 degrees is 1.699. So 1.699 times, I'm going to have to slant this down a little bit, the square root of S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. That's going to give me my confidence interval. I mean, again, I'm not going to take the time to type all this in, but you guys can plug and chug away in the calculator, no problem, I'm sure. So we find the 90% confidence interval goes from 3.83 to 17.83. Well, how would I do that on the calculator? Let's check it out. Remember that this is a 2-sample T interval. So stat intervals are all in tests. Let's go down until we see a 2-sample T interval. There's a 2-sample T test, but we're making an interval, not running a test. Here's a 2-sample Z interval. There's our 2-sample T interval. Do we have data or statistics? We do not have all the data from the trees in the list. So we need to tell the calculator we have statistics. Okay? What is X bar 1? Oh, it's 23.7 was the first mean. What's the first standard deviation? Oh, it's 17.5. Okay. What was the size of the first sample? Oh, it was 30. The second sample of trees had a mean of 34.53 with a standard deviation of 14.26. Oops, my decimal point didn't go in there. 0.26. And my second sample was of size 30. How confident do we want to be? We want to be 90% confident. We never, ever, never, ever pool our data. So always make sure it says no when they ask us to pool. And then we hit calculate. And we get an interval of negative 17.72 to negative 3.93. Slightly different than what we got here. And oh, that's because I forgot to copy down my negative signs when I did my calculation here. Okay. So why is it slightly different? Because the calculator keeps more significant digits than we can by hand. So when we have the calculator do all the work, it's running like 10, 15, 20 numbers behind the decimal point when we're plugging in only 2 or 3. So that's why the difference is what it is between the calculator and by hand. Either answer would be 100% correct and get you full credit on any test or quiz or AP test. So let's go back to our full screen here and let's finish up this problem. So we did it. We got the interval. What the heck does it mean? Well, we always start our interpretation this way. We are 90% confident. 90% confident of what? That the difference maybe I should say the true difference in mean DBH. Remember, DBH is just the mean diameter around the tree at breast height. Okay, the mean difference in the true mean difference in the DBH in the southern trees and the northern trees, right? So we are 90% confident that the true difference in the mean DBH is between 3.83 to 17.83 less in the northern forest than the southern forest. So we are 90% confident that the southern forest trees are somewhere between 3.83 and 17.83 larger than the mean of the northern forest. Or we can say it the other way. We are 90% confident that the true difference in the DBH, or the diameter at breast height, is between 3.83 less to 17.83 less in the northern forest than that of the southern forest. It doesn't matter which way you say it, as long as your interpretation is correct.